So in this video, I'd like to go over the following problem. We're told that there is a cannon. This cannon fires cannonballs. So here's our cannon, and this cannon is on a horizontal plane. We're told the inclination of the angle that the cannon fires projectiles. So let's assume it's theta. We're also told the initial velocity of the VO. We can put numbers in here. So for example, if this is, let's say, 30 degrees and VO happens to be something like 30 meters per second. Okay, so that's your initial velocity. So there's a projectile, and the projectile is fired, and we'd like to know the following problem. So it's some kind of a motion. It's actually parabolic, but so we'd like to find the number one, the height, the largest height that the cannonball reaches, and also I'd like to know the distance that the cannonball lands. So wherever the cannonball lands, I'd like to find the distance and the height. So we're told the initial velocity and theta, the inclination of the cannon when it fires the cannonball. So let me erase this so that I can actually start. Actually, let me keep this for a sec. So the equations I'll be like to go over, right, is, so our first problem is that we have a cannonball. Here's the cannonball. It's being fired initially from a cannon that is located at an angle theta. And so we know VO, we know theta, and so the question is, what is the VO vector? The initial vector. So we know VO. So if you think about it, so I'm assuming that we got familiar with the I coordinates and the J coordinates. So I'm going to assume that I is to the right and J is up. So usually I've used I to mean east and J to be north, but in this case I'm selecting I to be to the right, going this way, and up is J. So just to make sure you understand, so 2I plus 3J means that 2 units to the right and 3 units up. So this is our definition of the vector V. So how can we do this? So we need the x component, or the I in the I direction. So this is a cosine. So I'm going to put this as VO cosine of theta I. And it's going up, so in the opposite direction. So the ratio of this side to VO is sine. So this will be VO sine of theta J. So we have the initial vector. We also know that there is an acceleration, right, that is due to gravity, and we know this object, whatever is accelerating, it's pointing down. The acceleration vector is going straight down, so it's going down, and I'll use the quantity minus J. So the opposite of up is down, which is negative J, so it's minus G. Notice that we're using G to mean 9.8 meters per second squared at the surface of the Earth. That's the 2 significant digits. I'm not going to worry about the significant digits so much. I really want to make sure that you understand the basic ideas of constructing the solutions to this problem. And what else are we given? We have theta, we have the initial velocity, and how are we going to calculate h? Well, we have 2 equations to live with, right? We have one equation that basically says the 2 vector equations for constant acceleration, you should remember, is v final is equal to v initial plus acceleration times time. That's number 1. Number 2 is basically d final is equal to d initial vector plus v initial times time plus 1/2 acceleration t squared. Usually we had 3 equations to worry about in 1 dimension, but for as a vector equation where we work in 2 dimensions or 3 dimensions, we have actually 2 vector equations, and these are 2 vector equations I'd like to write. So let's start plugging it in. So let's take the first equation. So looking at the first equation, right, v final is equal to v initial. V initial is VO, so it's VO plus acceleration times time. I don't know what the time is, but let's plug it in anyway. Let's see what what we can get. So VO happens to be VO cosine of theta I plus VO sine of theta j, and that's VO. And the acceleration happens to be minus gj, so it's minus g j hat times time. And I'll break it apart into i's and j's so we can separate everything out. So in the I component, we have VO cosine of theta plus j hat, which is, oops, it should be a little more larger than the last earlier. So this is j hat. So j times VO sine of theta minus g. And that's your velocity vector anytime in the motion. Now let's ask ourselves, we don't have time. There's a t in here. I seem to have forgotten that. So there's a time in here. So when the projectile is projected straight up, what do I know? Well, I know at the top of the peak, right, the velocity will be horizontal and not vertical. And so I know the vertical component, but this is the up and down component, which is in front of the j, right? That has to be 0. So if I know that, I can actually solve for t. So let me erase some things here. So I don't think I really need this diagram anymore. And I should write these over again because I'll need them. So I'll put on the top left-hand corner, rewriting these. And let me get another marker. So here is VO. The initial velocity vector when the cannon is fired is VO cosine of theta I plus VO sine of theta j. Okay? And we also know the acceleration of the system, right, is minus gj. We have that g is 9.8. So I'll write that down just to remind you what these numbers are. We're also told that theta, I just selected arbitrarily 30 degrees, and we also know that the initial velocity VO is given by 30 meters per second. I've selected all these in standard units, so I don't have to keep track of the units. So here's our standard VO, acceleration, VO, and theta. So I think I've gotten everything. Oh, and of course, h is the height. I'll just call it peak. And what else? D is the actual distance to impact. Let's say impact. Okay, so I've written down everything, so I think I can erase everything, and so I have V final. So here's our first equation. So remember, there are two equations that we're going to be constantly using, right, are the two vector equations, V final. Can you see this on the board? Yeah. V initial vector plus acceleration times time, and the displacement final is equal to the displacement initial as vectors plus V initial times time plus 1/2 acceleration times t squared. So these are the standard equations that you're going to see constantly over and over again in terms of vectors. So these are the two vector equations you must know. So let me erase everything else. I don't think I need anything else. I've written down everything except the V final, so I'll keep that in mind. So let me erase this, and I'll rewrite this over here. So the velocity final for any time t is given by this expression. Maybe another marker would do. So that is V final is equal to the I component, which is VO cosine of theta. So it's important that you remember that we're never going to substitute actual numbers into these expressions, these equations, because we want to substitute in the last step. Here is theta minus g, and t. I don't know what t is because this is the velocity at any time t. So for example, if t is equal to 0, then we have the initial velocity just as the ball leaves the cannon, the turret of the cannon, the barrel of the cannon, when t is equal to 0. So our first thing we should notice is that, so just to remind you, so here is the cannon, fires the ball, and on the peak, right, let's call it T top. Well, let's make it T, or how about TH, T high. So all I know is that the vertical component, right, the velocity of the projectile at the peak motion, right, is like this. The velocity is going straight this way as it's falling back down. At that point, the vertical component, this component in front of the J, must be 0. So I know how to calculate TH. So let's do that. So what is TH? TH is time at peak. Okay, this is the time at peak, and we know what that's supposed to be. That's supposed to make this 0. This component has to be 0 because this is the velocity vector. Oops, I forgot my arrows. So I forgot the arrows there. So that must mean that VO sine of theta, notice I know VO, I know sine theta, minus G, TH is equal to 0. So we can solve for TH by moving this to the other side. And then divide by G on both sides to get T at H. So we have VO sine of theta, VO sine of theta over G. And so this is TH. And so I've just calculated TH. So I should put it somewhere that it's, so let's put it right over here. So TH, the time for the highest peak, the time for the highest peak, this is really bad. The time for the highest peak, TH, is given by VO sine of theta over G. So that's the TH, the time to the highest peak. Now all I have to do is, I have a distance equation, and that distance equation, let's go expand it. So our distance, right, d final for any time t is given by d initial, and just for simplicity, right, I'm going to take d initial to be the origin of the cannon. So if this is the cannon that's firing, I'll take di, the initial point is 0I plus 0j. So in that case, this is dropped, so I don't have to worry about it, but I'll put it in anyway. 0I plus 0j is equal to d initial. What is the initial velocity? Well, we already know what the initial velocity is. The initial velocity is given by here. Actually, did I write it down somewhere? Well, we can calculate it over again, but it's this component, VO cosine theta and VO sine theta. I should have written it down separately, but it's VO cosine theta, and so let's write it out. So this is really VO cosine of theta I plus VO sine of theta j times t. And then finally, the acceleration is 1/2, and if the acceleration is given by minus gj. Oh, I should put it right here. Here's our VOT. I was wondering where I put it. So here is minus gj times t squared. So we can actually separate everything else. So let's separate into the components form. So here's I. The I component, there will be a VO cosine of theta times t. So I'll put the t in front here. So there's a t in here. And then there's an I, there's no other I component, so I can just look at the j component. The j component basically has a VOT sine of theta. There's a j component here, and then there's a j component over here, which is minus 1/2 g t squared. Okay, so this tells me the position of the object at any time. So here is my, here's t. So this is the position to the right, and this is the up and down position of the object for any time t. Now, what I really want is the height where this object is, which is this component at th. So the height must be nothing more than this equation, which is VOT sine theta minus 1/2 gt squared, and this is at what? The height, at the time where the highest peak, so th. So now we have to plug in VOTH. We already have VOTH over there, so I know what this is, so let's plug it in. VO times VO sine theta over g minus 1/2 g times VO sine of theta over g squared. Okay, so let's put a line there. And do I have another marker? Okay. So we're over here. Let's continue this. So this is VO squared sine of theta over g for the first term. The second term is, actually, there's a g, there's a 1/2 in there, so I'll put the 1/2 out. There's a g and divided by g squared, so you'll get a g at the bottom, so I'll put that over there. 1 over 2g, and then VO squared sine squared theta. VO squared sine squared theta. And let's double check. VO squared sine squared theta. Yeah, looks good. So I'm going to factor out this equation and look at this and say that, so there's a sine theta, we can't do anything about it, and we can factor out sine squared g. So VO squared over g times sine of theta minus sine squared theta over 2. And I think that's the vertical displacement. So this is the height. So the height equation, right? Let's erase this over here. So this is a long problem, but you get used to it. You'll get used to it. H is equal to the height is equal to VO squared over G times sine of theta minus sine of squared theta over 2. Great. So this is where the height of the object is. So we can plug in numbers. If you know what VO is, VO is given by, oh, here we go, 30 meters per second, so 30. This is G. We have sine of theta and minus sine squared theta over 2. Okay. Okay, so this is where the height is. Let me just think. V final is sine theta. I'm double checking just to make sure that the equations seem right. So let's double check. If theta is 90 degrees, the projectile should be going straight up. So I'm going to substitute theta equals 90 degrees. Sine of 90 is 1. Sine of 90 is 1. So 1 minus 1/2 is equal to 1 minus 1/2 is 1/2. So there will be 1 over squared VO squared 2g. But then 2gh. So 2gh. VO squared is equal to, yeah, that's correct. So initial squared is equal to VO squared over G 2AD. Yeah, it's fine. V final is minus 2AD. Yeah, it's okay. So I just double checked with an angle theta is equal to 90 degrees, so this is 1, and it's going straight up. So I know the general equations for straight up, right, is v final squared minus equals v initial squared plus 2ad, and it seems to have the right form, so it's okay. So everything seems to be correct. So what happens if theta is equal to 0? If theta is equal to 0, the height is 0. Yeah, makes sense. So that's my quick test. I'm just doing this mentally in my head just to confirm if everything's okay. Okay, so so I've calculated the time for the peak. I'll write these things down so I can, yeah, I only have a short board, so VO sine of theta over G. So we have that height, and now let's calculate, we have this final equation, and I should write it somewhere, so I guess I'll, here we go. So let me write it over here. So for any time, df is given by I. So this is the displacement at any time. So remember, this is difficult for everybody. So don't think that this is easy. It's difficult for me too, to go through, do these calculations, but I'm mechanically following the, and I might make mistakes, but I'm double checking. Okay, great. So the next order of business is, where does it land? So I think I've copied everything down correctly, VO squared, so I think I've copied everything down. So I don't think we need anything up to here, right? So let me erase everything over to here. So remember, these are some of the most difficult problems in your university physics class. But okay, so we now have an equation. So let's think of the problem. The next problem is I'd like to calculate the d where the projectile lands. Now, if you look, this is for any time t, right? This is the equation. But what time does it land? Well, the time it lands, right, must be when it hits so its position as it travels, right, at t equals 0, starts at the origin, 0, 0, and then is some kind of a trajectory. It's actually, it's parabolic, but let's not go through into that. It's not important. So right now, the trajectory is some trajectory. It hits this point. But that point, right, means that the up and down direction is 0. The y-axis is 0, which means that this is equal to 0. Let's call t, let's call it t, what do you want to call this? T, I already used h for high, so maybe TL for low. So TL is the time of hitting ground. Let's just say time to ground. Let's make it really simple. So this is TL, time to ground. So this TL, right, how do I calculate it? Well, this occurs when we reach this point, right, when this is 0. When the J component, the horizontal component we don't know, but the vertical component, it reaches, there's the vertical component, it reaches 0. So this term must be 0. So therefore, VOT sine of theta, and this is TL, time to ground, I guess. Maybe we should call it TG. Well, it's too late now. I call it time low. TL sine theta minus 1/2 G TL squared equals 0. We have to solve for TL. So if you factor out things, right, you'll notice that TL comes out of VO sine of theta minus 1/2 G TL equals 0. And if you think about it, there's two possible solutions. Either TL is equal to 0, which means it's at this point, or TL is at this point, which means this is the other term. So it must be in this term because we really want this term right over here. So this must be VO sine of theta minus 1/2 G TL is equal to 0. Because we already know TL can be 0 over here. Now I'm going to move everything to the other side and solve for TL. So it's on this side, and multiply by 2 divided by G. So this is really 2 VO sine of theta divisible by G. This is the time to hit the ground. but if this is the time to hit the ground, right? But I know the position, this is the x and y coordinates, right, of that object. So this position of this object is really the x coordinates corresponding to this is d. So d is equal to VO t cosine of theta, and this is supposed to be TL, right? So we can plug in TL. So this is now VO times 2VO sine of theta over G times cosine of theta. And so we can get, so we'll bring the terms out. So this is VO squared 2, there's a sine theta cosine of theta all over G. And if you kind of remember, okay, this is kind of a little more advanced, right? But if you remember what 2 sine theta and cosine theta is, it's actually the sine of, it's your double angle formula for sine theta. I won't actually say it, so this is actually VO squared over G sine of 2 theta, but I won't reduce it. It's not that important. But the main thing is you now have equation for D. And we know what VO squared. So in the last step, right, you should actually be substituting in a calculator. You say 2 times VO. VO happens to be 30 squared sine of 30 degrees cosine of 30 degrees over G. And remember, 2 sine theta cosine theta is actually sine of 2 theta. So this is actually, but this is not important. Once you get this equation, right, what you're doing is, anyway, so we could write this in terms of VO squared, and this is not necessary. If you happen to remember it, that's nice, but if you don't, it's fine too. So here is 2 theta. So 2 sine theta cosine theta is equal to sine of 2 theta. You might remember it from your math classes, you might not, but that's not important. You already have an equation for the distance. So we have a distance for the height. We can plug in for different theta. We have an equation for distance. So this is all coming from our understanding of vectors and applying it to this point. So the actual derivation, it's very mathematical and it's kind of painfully long, but this is, these are a couple of problems that are much more difficult in your course. So I'm doing it so that you can actually see the steps, but the main thing you should always remember is that the 2 vector equations that we always will need, right, is these 2 equations. V final is equal to V initial plus acceleration times time, and D final equal to D initial. Oh, sorry, I seem to have forgotten the arrow over here. Little mistakes here and there, but there's an arrow, so there's the 2 equations you have to know. So this problem is for solving a cannon that's inclined at an angle theta, firing a ballistic projectile, and where it lands and what's the height that it reaches.